Madhur, let's get started.
Sure, Abhijit. Well, good afternoon, everyone. I hope you guys are doing fine, doing good. The topic for today's discussion is Introduction to Big Data Ecosystem. So let's get started. To begin with, what the first question should be like, what exactly is big data and how much GB of data should be qualified as big data? So if you look at the image on the screen, and if you start from this bottom and go up to 100 GB, you would realize that for every such value on the left hand side, we have this value of PostgreSQL on the right hand side, which is the traditional relational database. It is not big data. And what that means is that even if your data is of the scale of 100 GB or some multiple of 100 GBs, your traditional relational database is capable enough to handle that much amount of data. So when should one consider migrating to big data? So to understand this, let's consider a couple of scenarios. So there is this business A, which comes to me and explain me his scenarios. So he has certain use cases. Like he tells me that he has 250 GB of data. The data is well structured, and the velocity at which the data is increasing is not that huge. So today the data is 250 GB. It's possible that even after 1 year, the data is something around data would be something around like 275 GB or 300 GB. So the velocity is not that huge. And in addition to that, he tells me that he has this amazing team of backend engineer who are like SQL vanguards. They know in and out of SQL and can write very performant queries. They are really good in data modeling and indexing and joins and everything. And the best part is the business is working really fine. The end customers are really happy. So if that particular business comes to me and asks me, should they consider, moving to big data ecosystem and should they consider migrating to big data? To that particular business, my solution would be no. You don't have to, unnecessarily complicate your existing architecture. You don't have to, migrate to big data because your customers are happy and, you have this great team who are capable of handling this big amount of huge data. Then you don't have to unnecessarily complicate your existing architecture. Now consider this another scenario where I have this business B who comes to me and explains his use cases. Like he has 250 GB of data, but the problem is this data is not structured. Some of it is structured, but then there is this another huge chunk which is semi-structured or non-structured data. On top of this, the data at which it is scaling right now, it's going to shoot up considerably, maybe in a year or something. So today the data is of 250 GB. It's possible that down the line it's going to be 1 TB and more. And another thing is this particular business does not have any strategy right now, like how they want to consume this data in the future. Like right now, they don't have any strategy, but maybe in the future, they will somehow capitalize on this data. So
It
should
is
they
scaling.
consider migrating to big data ecosystem and should they start using big data technologies? To this particular business, my solution would be the sooner they migrate to big data ecosystem, the better it would be for their company. So assuming for we have, going forward, assuming we are dealing with big data, and let's get started. So let's say we have this huge chunk of data which can be in the scale of terabytes and more. So the first thing is, how do we handle this much amount of data which is so huge and so scalable? So the first couple of challenges that we face while dealing with big data is, how do we store this much amount of data? Because we are already dealing with hundreds and thousands of GBs of data. So how can we efficiently store this much amount of data? And it's not just about data storage, it's also about data retrieval. How efficiently and how easily can I retrieve this data when I want to, capitalize on this data? So for such scenarios, we have a couple of solutions. Either we can go ahead with data warehouse or we can go ahead with data lakes when it comes to, storing big data. And of course, we are going to look more into details like what exactly is data warehouse or what exactly is data lake in further slides. And the second challenge we face when it comes to dealing with big data is computation. Let's assume we have figured out storage, but what if we cannot perform calculations on this huge amount of data in the prescribed time? Let's say I have this, let's say I can, within 5 minutes I can retrieve all my data from the hard disk, but it takes like 4 hours to run a particular job. But my business requirement is that it should be completed within 2 hours. So Competition is equally important when it comes to handling of big data. So these are the two challenges which we are going to look into further details throughout the tech. So let's get started with storage. So what exactly is data warehouse and what exactly is data lake? So on the left hand side, we have this data warehouse, and on the right hand side we have data lake. So when to use is the question. When to use which one is the question. So assuming you have certain strategy in mind and you have some teams who wants to capitalize on this data, that means if there is this team of data scientists and there is this team of data analytics or BI team who wants to consume this data, what that means is they have certain amount of strategy how they want to consume this data. That means we have a schema in place. So this teams like data scientist and data analytics team or BI team will, they will get in contact with the data engineering team. They will provide the necessary schema, and data engineering team is now responsible to, get all this data from remote locations, perform ETL tools, perform ETL jobs on this, perform some necessary transformations, do the data cleaning, and at the end, to transform the data which would be in sync with the schema which was defined by the data scientist and the BI team. What that means is when I want to consume the data from the data warehouse, I have a schema already in place. That means it follows a schema on right architecture. So I would prescribe, if business have already some strategy how they want to consume this data, they should go ahead with data warehouse. But it's totally possible that business does not have any strategy right now, but they are collecting lots of data from various data sources. It can be multiple data sources, and it's possible that data is not structured, and right now they don't even have any strategy how they want to consume this data. So what should be the solution in that particular case? Then the solution would be create a data lake, dump each and every part of the data in that data lake. And maybe in the future, once the data scientists and BI team have come up with some strategy, at that time, define this data, define a schema at the time of reading the data. So this particular paradigm is called schema in read. So what that means is when you are creating data warehouse, you are using a schema on write paradigm, whereas when you are dealing with the data lakes, you have this paradigm of schema on read. And if you check at the data, this particular data looks very much organized because we have well-defined schema. Whereas if you look at this particular data, the data is highly disorganized because we don't have any strategy right now. We are just dumping the data into the data lake. So what that means is if you have some strategy, go ahead with data warehouse. If you don't have any strategy, but you just want to write to the data, go ahead with data lakes. So if you want to further deep down on this particular topics of schema on read versus schema on write, you can always check out this particular link. Throughout the deck, I have added few such slides where I have just shared few links with the end users and with the audience who can further deep down on those particular topics. Now, before I jump to the computation part, I would like to discuss this another topic, which is again very relevant with when it comes to big data storage, and it's the topic of columnar storage. And what's the significance of columnar storage when it comes to designing data warehouse? So let's assume I have this table called table_1, and I have just 3 columns in the table, A, B, and C. And A1, B1, C1 is the data, A2, B2, C2 again is the second row of the data, and A3, B3, C3 is the third row of the data. Now, if someone comes to me and tells me, hey, Mother, I want to store this data on the hard disk, what's your approach is going to be? So the most basic approach which I can think of this is I will take this data one row at a time. Like first row is A1, B1, C1. I will take that row and I will store that in block 1. Then I will go ahead and take the second row and I will store that data into block 2. And same is the case with row 3 data as well. So this is totally fine, and everything is realistic with this approach. And in fact, most of the relational databases work on this approach, and there is nothing wrong with this approach. Now let's try to run a certain query on this particular approach, the approach in which we are storing row-wise data in the blocks. So if I try to run this particular query, which is select B from table underscore one. Now, how is that query going to run? Now, let's say I want to select all the values for B column. What I would do is I would go to block one and I would pick the B1 value. Then I would go to block two and I will pick the B2 value. Then I will go to block three and I will pick the B3 value. What's happening in this particular case is, irrespective of what your query is, to get the data, you will have to perform block reads and you will have to read each and every block individually. So if I have 100 blocks, if I have 1000 blocks, I will have to read each and every block. The thing is, the time taken for query completion is directly proportional to the number of block reads. So if I have to perform the more block reads, my time for query completion would be more, and that would certainly hamper my execution time for query completion time. That would certainly, hamper the performance of my query. So imagine you are in the big data territory, and it's totally possible that you have this table which is already consists of, let's say, 100 GB of data. That's totally possible. So to read even a single column of data, you will have to, perform all the block-wise read. That means you are going to read 100 GB of data, and of that particular 100 GB, you will just filter out some data. So this will certainly hamper my query performance, because even for one column, you will still have to, read 100 GB of data. Now, the solution to this particular problem is, instead of storing the data row-wise, we are going to store the data column-wise. So in this A column, I have this data A2, A1, A2, A3, and I took that data and stored in the block one. And same as the case with block two and block three. Now, what happens is that now when I run a certain query, like select B from table one, I will just directly go to block two and I will pick all the data from there. What's happening in this case is I'm not performing all the block reads, and because of that, the performance of my query is going to be highly optimized. So even if you're reading 100 GB of data and the table has, let's say, 100 columns, and you are just interested in one column of data, you are just going to perform 1 GB of data read, not 100 GB of data read, which was the case with row-wise storage. So I've already optimized my performance by multi-folds. And this concept of column storage is basically the basic principle behind all the data warehouse design. So if you consider Redshift or Azure data, Azure SQL or Snowflake, all of these databases, data warehouses behind the scene are working on this concept of columnar storage. In addition to that, we have this Parquet format, which is just another format for storing a file, just like CSV and text, but is widely used in big data ecosystem. So the Parquet files are also based on this particular columnar storage. So that's what we have in the storage part of the big data ecosystem. And to read more about columnar storage, you can definitely check out those particular links, and you will find something more interesting. Now let's move to the computing part of the big data. But to begin with the computing, let's try to understand the chronology of how things are happening when it comes to distributed computing. So to perform distributed computing, it's highly essential that you have multiple computers which are connected with each other, and each set of computers should have certain amount of data on which we can perform the calculations. That means my data set should be distributed. That means if I have this 1 GB of file and I have this 5 computers, then I should be able to split that 1 GB of file across this 5 set of computers. So that's the concept of distributed data sets. But to achieve distributed data sets, you need to take help of distributed file system. But what exactly is distributed file system? To understand what exactly is distributed file system, you need to know what exactly is file system. So let's try to get started. Let's get started with file system and what exactly it is. So file system is nothing but the logical abstraction layer on top of your physical storage. What that means is, let's say I want to create a file or directory on my computer. So while doing so, I never tell my computer, hey computer, go to this particular memory address on my hard disk, see if that block of storage is, I'm sorry, there is a call on my phone. I would just, reject that particular call. Sorry for the disturbance. Sorry for the disturbance. Okay, so we were talking about file system and we were discussing, like, let's say I want to store a certain file, or I want to create a directory on my traditional file system. So I don't, instruct my OS, hey OS, go to, so and so particular memory address and see if that block of storage is free or not. If that block of storage is free, create a file or read data from that file. What I actually do is I provide certain file path, or I provide certain directory path to my OS, and I tell, hey, go to this particular file path or go to this particular directory path and create a new file, or maybe read data from that file path. So what I'm actually doing is I'm providing a logical path to my actual physical storage space, to the actual physical storage device. So file system provides us this logical abstraction on top of your storage device, physical storage, and it also controls how the data is read, stored, and retrieved. So if I have this big file or movie file which is of say 800 MB, it's possible that file is broken down into multiple storage or multiple partitions, and each partition is being stored on the different blocks somewhere at a different location on my hard disk. But while storing that uh, movie file on my hard disk, I never have to care like which blocks are free and which blocks are occupied. File system takes care of that for me. The most common file system on your Linux file system, on your Linux distributions are ext4, and on the Windows is NTFS. And there is nothing wrong with this approach. They are very competent and highly do the work perfectly for which they are assigned. They can handle huge amount of data, but the thing is, there is a catch. They can handle this much amount of data, huge amount of data, but the data should be on a single node. So the moment when I decide I have this huge file, assume it's a 4 GB of file, which is a Blu-ray movie, and if I tell my file system, hey, pick take 1 GB of my movie and store it on your hard file system on your hard disk. But for the remaining 3 partitions, I want to store it on different hard disk. My existing file system won't understand this particular command because they don't understand how to store it in a distributed way. So to overcome the particular problem with the traditional file systems like ext4 or NTFS, we have to come up with the solution called distributed file system. Now, imagine a scenario where I have this 1 TB of file, which is totally possible in big data ecosystem. But the problem is when I try to store that this huge file on computers, there is one caveat. The individual storage on my machine is of 250 GB. So if I try to store this particular 1 TB of file on my storage, it won't be able to do it. So to give a solution for this particular use case, distributed file system is the solution. What it would do is it would create the blocks of your existing file, and it would send individual blocks on different nodes and will store that file in a distributed way. So that is what the use of distributed file system. And when it comes to distributed file system, the big data ecosystem, HDFS is our go-to solution. HDFS is the one which provides us distributed file system on the top of our cluster. So if you look on the left-hand side, this is our client, which can be your laptop, it can be your PC, and it wants to perform some read-write operations. It's possible that it wants to store huge file on this cluster, this whole HDFS cluster, which is running somewhere in cloud. It can be AWS EMR service, or it can be Azure HDN site. So we have already created this cluster, which is running somewhere remotely on cloud. So if I want to store, let's say, my file size is of 200 MB, and by default, my client is aware like what is the default block size of my HDFS, of my cluster. By default, the block size of HDFS is 128 MB. And my client is also aware of the replication factor. And what that means is when I store one block of data on my cluster, that data will get replicated that many times on my remote nodes. So in this particular case, I have this 200 MB of file, My block size is 128 MB. So by default, it will be broken down into two blocks. It will be block A and it will be block B. Now, my client will make a connection with this particular node, which is called name node, which also acts as a master for this whole cluster. So name node is the one which has all the necessary information about all the remaining slave nodes. So this, all the remaining nodes are the slave nodes. Name node does not actually store my data, but data nodes are the one who are responsible for storing my data. But name node is the one who has all the information in regards to data nodes. It has all the information like which data nodes are right now running, which data nodes are are down, or which block of memory is occupied on which data nodes and which blocks are free. It has each and every such metadata. So what my client will do is, it will, for storing block A, it will make a connection with this master node, which is name node. In return, if my name node finds that he can store this much amount of information on one of the data nodes, so it would revert back my client with the memory location on which particular data node it can store the data. So if so, and based on the replication factor, in my case it is 3. Name node will send the 3 addresses of data nodes. So once my client has procured all the addresses where it can store that particular block, it would make a connection with that data node and directly store that block of data on that particular data node. And this is how, if you can see, block A is getting replicated multiple times based on my replication factor. So this is the very basic overview of how this HDFS distributed file system works. Now, to get into more details, these are a few of the links which I would strongly suggest that you should definitely check it out. This particular link is for AFour specific because it's a data which is only people from AFour can access, and this is some of the documentation which is shared internally within the data engineering team. But for rest of the people, these are a few of the resources which you should definitely check it out, and these are a few of the keywords which can help you further deep dive on this particular topic. Just to point out, this particular big data Hadoop administrator course, this particular course is right now freely available on this particular app called Simply Learn. Simply Learn, it's a mobile app which has some premium content, but just because of COVID-19, they have made some of their courses freely available. So big data Hadoop administrator course is one of them. And I would strongly suggest, if you want to see like what's happening in the real world, like how the cluster is actually getting created, how you create multiple virtual machines on your system, and how you make each of those virtual systems connect with each form contact with each other, and how you create the name nodes and how you create the data nodes, I would strongly suggest you should check that particular course. In addition to that, there is this particular HDFS comic, which without getting into much details, covers the whole basic architecture of HDFS in a very efficient way. So I would suggest you should check out the resources. Now, moving forward, so far we have done like how the storage is handled on big data ecosystem. But what about the resources? Because we are already dealing with multiple nodes. It can be 100 of computers which are connected with each other, and each node has some certain amount of CPU processor running, which has certain amount of cores. Each node has certain amount of RAM. So we will need something which can manage all these resources. Now, to think what's the role of resource manager is, let's try to understand what's happening in traditional systems. In the traditional systems, like our laptop, on the very basic level, we have our hardware, which consists of storage. It can be hard disk, it can be RAM, and it has processors, which are ultimately, responsible for performing some computations, running your threads and processes. On top of this hardware layer, we have this OS, which is basically a software interface on top of your hardware. So OS is the one because of which we can communicate with the underlying hardware. So to communicate with the storage, OS provides us with file system, which we have already seen in the previous slides, like what is the role of file system and what's the role of HDFS. But there is more to it. OS is also responsible for performing all the resource management on your system. Like it is it does know like how many cores are there on your system, how many cores are busy right now, how many cores are not occupied, how many cores are waiting for some work to be assigned. And accordingly, based on that resources, OS is also responsible for scheduling tasks. So based on the available resources, OS will perform certain tasks. And on the most topmost layer, we have our applications running. It can be anything. Now, if I take this model of traditional data or traditional systems, and if I try to replicate this model on the distributed system, let's see what we get. At the most bottom layer, just like we saw, we have distributed hardware. It can be 100 computers connected with each other. Each node will have certain amount of storage and processor. But on top of this, we have this concept of logical OS. It's logical because there is no such OS for distributed systems. It's just a logical thing. So this logical OS will be responsible for performing this OS related task. First one is file system, and we just already saw like how HDFS is responsible for performing the file system related task, how HDFS can efficiently handle this file system related task. But to perform this particular task of resource management and scheduling of the different tasks, we have to make use of another tool which is called Yarn. Yarn is yet another resource manager, which is basically responsible for performing all the resource management and task scheduling related tasks on distributed systems. So most likely, if you are ever going to interact with a big data ecosystem or some cluster, it's highly possible that behind the scene, Yarn is the one who is responsible for managing all these resources of your cluster. And on top of this, we build applications, and these applications are generally built using Spark or Hive, and there are many different sets of technologies which can, interact with this distributed file systems or distributed system. So this is the whole basic idea behind like what's the role of resource manager and what is the responsibility of Yarn. Now let's take a basic let's take a look at the architecture of Yarn. So here we have a client. Most likely this client is going to be some Spark job, or it can be MapReduce job, or it can be some Hive query. This particular client wants to run some code into distributed fashion. That means the computation should happen on multiple nodes. So this client will submit that particular job to our resource manager, which is Yarn. Now, Yarn has two components. First one is Yarn scheduler, and the second is application master. Application master is the one who is responsible for accepting this submitted job and negotiating necessary resources to launch that application. Concentrate, we are not talking about running an application, we are just talking about launching an application. So when my client submits a job, it also specifies certain attributes like how much core is necessary to launch an application, how much amount of RAM is necessary to launch an application. And based on that specifications, my application manager will negotiate for a container with this Yarn scheduler. If Yarn scheduler is like the master who is aware of everything on like what's happening on the node. He's aware of all the nodes which are running, and he has information of everything, of every metadata, like how much RAM is available on node A and which particular task has been running on particular node B. So everything. So application manager sends a request to Yarn scheduler. If Yarn scheduler thinks that yes, this particular request can be approved, it would send an address of one particular node where this application manager can launch an application. We are not talking about running an application. We are just talking about launching an application. So once this particular application is launched, this application master process starts running on my node. And this application master is like a daemon process, which would be responsible for performing all the application related tasks on different nodes. So while launching the application, my application master knows that, hey, for running this particular application in distributed way, I would need two containers. each container should have this much amount of RAM, and each container will need this much amount of cores of processor. So this application master will go to the yarn scheduler, and it would make request for this bare amount of containers that is required for running the code on this nodes. If yarn scheduler thinks that yes, this request can be approved, in return it will send the address of the node managers, and this application master will go to that particular address where that node is running, and it will make a request to the node manager asking for a container. Now, this particular node manager is responsible for creating a container, and once the container is created, the command gets back to the application master, and application master is responsible for running that piece of code on the container. And this is how the whole process is running behind the scene for yarn architecture. And I can on this particular slide, I have provided you with the basic description of what are the different components. Like we have client, like we have node managers over here, we have resource manager, this particular block of data. So what are the individual tasks of each component? I have shared with this, I have provided on this particular slide. You can go as per your convenience. Whenever you find time, can you read all those different blocks? And this is the basic information. Some external resources which you should consider checking out for further deep down on this particular topic. And again, this particular resource is AFour specific. People from outside cannot access it. And again, this particular data, document is internal documentation within the data engineering team. And these are few of the resources or few of the tags, keywords which you should definitely Google just to get more information on what exactly yarn is and how the things are working behind the scene, because architecture is not this simple. There are many layers to it, but I'm not getting into all the nitty-gritties. This is just a basic overview of how the yarn works and what's the role of resource manager. But to deep down on further, you should definitely consider checking out this particular keywords. Now, so far, we have dealt with the logical OS part. We have looked at like what HDFS is. We have looked like what exactly yarn is, what are these responsibilities. And by combining both this, we have built a logical OS. And what that means is, if you are trying to build an application, say Android does application, it's essential that you first are acquainted with what exactly Android is. So right now we are just getting acquainted with what exactly Android is. But to build application on top of Android, there are so many different things which plays an important role. Like you should have good amount of expertise in Kotlin. Maybe you should know some front end frameworks and related libraries which can help you create those applications. Same is the case with distributed systems. Right now we have just covered the logical OS, but actually develop something concrete on top of this, like we have just covered till now the basic building block of distributed systems, but to actually build something concrete on top of this, it is necessary that you are aware with some applications, you are aware with some libraries which are being used to do build applications and do distributed computing. So these are a few of the libraries which I would strongly suggest. If you get time, you should check it out. One such library is Spark. So if you ask me, just give us one technology which we should consider getting started with. So I would suggest you should definitely consider learning Apache Spark, because it's a beast of a technology. It has so many different components, and it can handle so many different kinds of data. It can perform batch processing. It can do stream processing, where the data is coming in real time, and you are capturing those data and performing computations in the real time. It also has a support of ML libraries where you can actually code on machine learning algorithms. So I strongly recommend that you check out Spark if you want to just get started with this data engineering basic building block of distributed applications. But in addition to this, we have other technologies like Hive. Hive was started back in, I guess, 2005 or six at Facebook. It was their internal project. And the idea was that to actually build an application or to perform some computations on distributed system, it was very essential that you are either acquainted with Apache Spark or MapReduce of Hadoop. But to write code in those particular languages, it was essential that you should be aware with either Scala or Spark or Java. Either Python, Spark, or sorry, either Python, Scala, or Java. But the problem is the people who are coming from the SQL background, they are not aware of those programming languages. Generally, they don't do anything with those programming languages. They are very good in SQL, and that was the whole concept behind building Hive. What Hive does is it provides you with a query language called HiveQL, which lets you write SQL-like queries to perform computations on top of your data. So what actually happens behind the scene is, even if you are writing SQL-like queries, behind the scene, those queries are getting converted into MapReduce jobs or Spark jobs. So you get the best of both the worlds. At the front end, you are just writing SQL-like queries, which are generally the backend team is comfortable with. And behind the scene, those queries are getting converted into optimized, MapReduce jobs or Spark jobs. In addition to this, there is this library called Apache Kafka, which is again highly proficient and go-to library when it comes to consuming stream data. So if there is this thermostat which is installed at your house, or there is some IoT device, or maybe some your Twitter feed, and if you want to consume this data in the real time, Apache Kafka is one such library, and it's a go-to library generally when it comes to consuming real-time data. In addition to this, there is this another library called Presto, which was again an internal project as Facebook and was recently open sourced, I guess, back in 2017. And it's a library which is similar to Spark, can handle huge amount of data, and it can be, data can literally scale up to 1 petabyte, and it performs all in memory calculations. So the data speed is huge. So this is another one such library. But the thing with Apache Spark is right now it's the industry's go-to library. And since every company or almost everyone is using Apache Spark, it has got tremendous amount of support from the different cloud services. And most likely you won't be developing your cluster on your on-premise server. It's highly possible that your cluster is deployed somewhere in cloud. So to play around with cluster, different cloud services have different cloud providers have different services, and which lets you interact with those cluster. So in case of AWS, we have the service called AWS EMR, Elastic MapReduce, which is behind the scene running on Spark. In case of Azure, we have the service called Azure HD Insight, again behind the scene running on Spark. In addition to that, we have this company called Databricks. Databricks was the one who was originally responsible for, they were the one who actually developed Spark and made it open source. And Databricks, and then they went on to create this commercial company called Databricks. So the founders of Spark are actually working at Databricks, and Databricks is another this company which provides cloud-based solution. Behind the scene, those cloud is actually working in AWS or Azure, but on top of that, they put their own layer for performing distributed computing. Now, to get your hands on or get some information on Spark, again, this link is AFour specific. It's a very comprehensive documentation. Like there are close to almost 30 to 35 pages for this particular topic on this particular Spark basics and its architecture. And it's a still work in progress. Like as and when we are learning new stuff, we keep adding to that documentation. But for other people, these are few of the links. It also points to some of the playlists which are available on YouTube. You can consider checking this out. And in addition to this, we have certain keywords which, again, based on your convenience, if you are thinking, if you find this particular topic interesting and if you want to deep dive, you can always check these keywords for more comprehensive knowledge. Now, I understand, like right now we are going through a really tough phase, and everyone is facing certain issues, but still, there are few websites who have made their content for freely available just for this certain span of period. So there is this website called Plural Site. It's a website which is similar to Udemy or Udacity. it has number of video courses, and generally the content on this particular site is very high quality and highly sophisticated. And because of COVID-19, they have put their whole libraries of almost close to more than 7,000 videos of freely available for the whole month of March. So you can go to their website, just sign up on that particular website, and you have free access to number of courses. In addition to this, there is this website called Real Python. If you are interested in Python and if you want to build your skill set in Python, I would strongly suggest that you check out this particular site called realpython.com. They have really good tutorials, blogs, and those blogs are very in-depth, provide you with in-depth knowledge. And in addition to that, they also have some video courses which is not free, but again, because of COVID-19, they have put there some modules, some of those modules of video courses freely available. So if you go to a particular website which is in this particular link, you can always check that particular you should also check that website as well. Now, in addition to that, Sundar Pichai last week made an announcement, like he had aggregated number of data sets which are related with COVID-19, and you can use that data sets to build your big data query skill set. So the thing is that BigQuery is Google's answer to data warehouse. If you want to perform data warehouse related stuff on Google Cloud, you will choose BigQuery. So using this particular data sets, which are right now available on Google Cloud, you can run any number of queries and Google won't charge you for those queries. So you can go and subscribe to Google Cloud and run those queries using the data set of COVID-19 and come with some exciting results. So these are few of the resources which are right now available for free. If you get time, if you have the privilege of free time, if you can afford some free time, and if you want to just upskill your existing skill set, you should check this out, check out the sites. So I guess that's it from my side for this particular talk. Any questions?
Madhur, there is a question on chat.
Yeah, sure.
Which are top data lake tools and data warehouse tools?
So for data warehouse, you can choose Snowflake, which is another company just like Microsoft Azure and AWS. So that is one solution, Snowflake. You can choose Redshift, which is AWS solution to data warehouse. So Redshift is one such solution. Then Microsoft has its own solution which is related with data warehouse. I can go to a particular slide and I can show you. So these are a few of the vendors. Google has a solution in the Google has a service called BigQuery, which provides the data warehouse service on Google Cloud. And when it comes to data lake, so Microsoft have the service called I cannot remember, but then I'm pretty sure Microsoft have the service which lets you build data lakes. In case of Amazon
Azure Data Lake.
Azure Data Lake. And in case of AWS recommends that you should use S3 for storing any kind of data. So you can use S3 as a data lake. And in addition to this, Databricks also has a service called Data Lake, which is built on top of, like we already discussed, Databricks is the one who provides with all the solution for building distributed systems. So it is built on top of those existing systems, and it can also be used. So the service name is Databricks Delta Lake, which can also be used for building data lakes.
Hello.
Yeah. Hello. Abhijit, can you hear me? Hello. Hello.
Madhur, I can hear you. So maybe Abhijit is having some trouble. So let's wait.
Okay. Yeah, understand. So that's what we have in this particular talk. Any further questions?
I think we are good.
Sure, Abhijit. Okay, thank you.
Thanks, Madhur.
Thanks, Madhur.
Yeah, sure. Yeah, bye.
Thank you, Mother.
Sure.
Thank you, Madhur.